Hello and welcome back. If you follow the channel, you know that we are trying to replicate the famous Haffler and Keating experiment that directly measured time dilation as predicted by Einstein's theory of relativity by flying 4 HP 5061A atomic clocks around the world in 1971. Like Haffler and Keating, we can't just use one clock to give us the needed precision. Instead, we need to average a gaggle of clocks. And getting several of those tired clocks to work at the same time is proving to be challenging. We already had to repair 2 of them in the previous episodes. Not that they don't work, our 4 clocks now start up and lock on their cesium atomic lines as they should. And in ordinary lab applications, they would function admirably, outperforming GPS discipline clocks, even the expensive rubidium kind, by orders of magnitude. But in order to measure relativity, we need to push them to their limits, and in time clock parlance, that means that we need to achieve better than 10 to the minus 13 Allen variance at 100,000 seconds. That's technobabble for simply saying that any 2 clocks should stay within a few nanoseconds of each other over 2 days. So in the previous episode, we put together a metrology setup made up of a glorious pile of our best vintage HP equipment, which would have cost the equivalent of $250,000 back in the day. And the setup worked beautifully, too beautifully even. It revealed that our clocks were drifting more than we expected. Once again, this is all relative, we are talking only several tens of nanoseconds. But we now are in the business of splitting hairs, and that's too much for detecting relativistic effects. So we deep dive into the intimidating clock innards and had 2 bouts of complicated repairs. It paid off. The clocks got a lot better and we achieved our first good long-term stability curves in the last episode. Hooray! However, it's still not all rosy. As I repeated the long-term runs between several clocks, I noticed an annoying reproducibility issue. By the way, when we got our first not so good results, many of you worried that this might have to do with the measurement setup, temperature, interference between the clocks, external magnetic field, or other things that would affect a common quartz oscillator. But it is none of these simple things. None of these effects bothers the quantum spin properties of our cesium atoms, nestled inside the ultra-high vacuum magnetic shielded cavity. The cesium quantum resonance is given to us by nature. It doesn't age and is only limited by our ability to measure it properly, which is why it is the current definition of what time is. Sadly, it might simply be that our tubes are old and noisy, limiting our measurement precision. The cesium tubes have a finite lifetime, which is not that long, on the order of 10 years, after which their signal-to-noise degrades, and so does frequency stability. That's why these clocks were available on eBay for a few thousands, whereas a new one, yes, these are still made today with the same tubes, will set you back about $50,000. But I think there might be something else going on. See, there is one knob that you need to tweak to get the ultimate precision out of the clock, the C-Field adjustment knob. In a previous episode, we had explained how this magnetic field, about 1/10 of the Earth's magnetic field, needs to be precisely adjusted in a cavity. And we had adjusted it properly following the lengthy HP procedure, which uses the cesium atom itself to probe the C-field using the Zeeman quantum effect. Also, all explained, quantum physics included, in a previous brain-numbing episode. But the standard Zeeman alignment procedure is not good enough for what we want to achieve here. We are going to the absolute limit of what these clocks can do. So I had to tweak that knob even further to within a single graduation to make all the clocks match over long periods of time. And as I readjusted the C-field and made successive check runs, I started to realize that this did not lead to reproducible frequency shifts, as it should have. So doubt started creeping in my mind. I have become a time nut, and I am now doubting everything. Would my C-Field control circuits not be working as accurately as they should? Our experiment depends on it, so we better find out. Alright, I'm back with the atomic clock and it's on at the moment and locked, and I really suspect something's wrong with the C-field, or it's not as good as it should be. And conveniently, I opened it up and there's a test point for the C-field and it confirms my hunch. It's all over the place, and it was at 14.5 when I started, and now it's 15.25. And if you look over at the scope, it's super noisy. It's atrocious. So here we go. That's the level it is. And then when you tune it, when we do one graduation, it's tickling that decimal here, which is completely unstable. So I think that's my problem. There's an issue. Either the C-field, the way it's designed, wasn't stable enough. That's one of the things that was redesigned into the next generation of clocks. So it might be that it wasn't good to start with, or it has just degraded to the point where it's not regulating properly anymore. Right, time to look at the power supply board, and I've already partially extracted it. It's this beautiful fellow over here. And here it is on the bench, and surprise, actually I should put them the same way. It's not the board that's in the 1978 manual. Yeah, you can tell it's still the big cap over here, but this section is entirely different. And the entire power supply is completely different, which is an issue because I expected it to be something like this, and this design uses an early op-amp, an early transistor, so that's probably quite noisy. And then it took its reference voltage from this, just a simple zener. So if this zener has a problem or moves around, it's not going to be very precise. For a design that's stable to the fourth decimal, I would have expected a proper voltage reference source. And guess what? On this design, there is a proper reference source, voltage source. Yeah, I spied it right there. This guy is a 10 volt reference source. And there are a lot more ICs, so I think this one, they knew about the problem and they fixed it or attempted to fix it. But I have no idea what the new schematic is. Alright, I am making progress here. I didn't find the exact schematic of my board, but I found a schematic of a later board that's in the HP 5061B. And I was just looking at the schematics, and in this one it seems like they use the same circuit for the current source, which is a classic one. No op-amp, followed by a transistor, followed by a measuring resistor here that measures the current, and it's compared to a reference which now is properly derived from our 10 volt reference source IC. If this is the same circuit, they have done it the right way, and it just shouldn't move. It should be stable. Let me investigate further.
Moments later.
So I think I got a good handle on it. It's a mixture of old and new. It's somehow midway between the original HP 5061A and the revised 5061B. There are a few components that are outside the board that I need to add to make that work on the bench. So I'm just going to do that and see if we can reproduce our problems on the bench. So here I have the external power regulating transistor. This is my stand-in for the coil, the 1 ohm resistor. And then I have to wire the control potentiometer. I should be able to power up the part of the circuit that does the C-Field control. So that's ground. That's 29 volts. At first it didn't work at all because I put the transistor the wrong way. Now I've fixed that. So I'm going to go behind the camera here and try to get it started. So I'm going to bring it up slowly with the input voltage. At first it starts good, right? I am at about 14.7 volts on the input, and I keep going, and it should, here we go. Oh, it almost did it. So it went to 18.4, which is almost what it should be 18.7. And right now I am powering it up with 20 volts. But in normal usage, the input power that comes out of a transformer is 29, or out of the battery. So let's go there. You see how it started to oscillate and then it crashed? And then I can go back down and it will recover. There we go. And I can do it again. Boink. It's oscillating. Alright. Now, the reason it sort of worked into the device is that if I load it really hard, so here I have a 100-ish resistor for load, and here I'll put a 10 ohmish resistor for load. And now I can bring it up almost all the way. Yeah, it stays. It's at 18.63, and this is all my power supply can do. It can do 28.2 volts under that load. It's correct, but something is cheaty. It should, it's a linear power supply at lower load. It shouldn't have gone into oscillation. Which brings us to our elevator music section, where we will be exploring the schematics of this power supply. Our C-Field regulation circuit is over here on the right side. It's a conventional constant current source design. The C-Field itself is produced by a coil located inside the cesium tube. The current going through the C-Field coil is taken directly from the main power supply rail, but is tightly regulated by transistor Q11. On its way to the coil, the current passes through resistors R21 and R19. They have an asterisk in front of them, which tells us that their values are factory selected. These resistors produce a voltage proportional to the current passing through them, which is brought to one of the input pins of comparator U2. It is compared to a reference voltage set by the C-Field potentiometer. This reference voltage should be ultra stable, as it is itself obtained by dividing the voltage from U5, our 10.000 volt voltage reference IC, a new feature that was added in our upgraded board. We are sure glad to have this newer board. The output of the comparator then controls transistor Q11. This loop guarantees that the drop across the current sensing resistor always matches the reference voltage set by the C-Field knob, thereby regulating the current through the C-Field coil. But before we can check our C-Field regulation circuit, it looks like we have an even bigger issue on our hands. The main supply voltage rail, nominally at 18.7 volts, does not appear to be properly regulated at all. The voltage rail should be regulated by power transistor Q1, but something is seriously wrong with that regulation. The supply drops and even goes into oscillation at lighter loads, which it should definitely not do. So let's focus our attention on that primary supply. It is accomplished by not just one, but two regulation loops. The primary loop reads the supply output voltage and brings it to comparator U4, which compares it to a reference voltage once again derived from our ultra-stable 10-volt reference IC. The comparator output controls transistor Q1 via transistor Q3, completing the regulation loop. But there is also a secondary loop, which is the current limiter. Comparator U3 measures the voltage across the 0.1 ohms resistor R27. This low-value resistor is placed on the output voltage rail and continually measures the current drawn from the supply. If the current gets too high, comparator U3 will take over the regulation by pulling down the reference voltage at U4 via diode CR9. We have now transitioned to constant current regulation. That's done to prevent damage to the supply and other clock circuits from an overcurrent. Clearly, one of these two loops is not functioning properly. Problem is, at this point, we can't tell which one. Alright, I think I have an inkling of what's happening, or at least how to try to debug it. In this new circuit, there are two loops. There is the main regulation loop, which is here. It compares to the voltage reference, which is 10 volts. And there is another regulation loop that goes here, and this one looks at the voltage across the power resistor and limits the current, and one of the loops is not working. I think it's the one for the current limiter. And the good news is that the voltage reference, it works. It should be 10 volts, it's 9.9991 volts. On the scope, I have hooked up the output of the current limiter, and I'm going to power it higher and higher, boom, and it current limited right here. And that's when I hit about 21.7 volts, and that's when my power supply starts not working. It's hard to know if it's a cause or an effect, so the best way to test when you have circuits in a loop is to remove one of the loops. I'll just desolder this diode, and that's going to take out the current limitation and see if it works if I do that. Loopy circuits are notoriously difficult to debug, and one of my favorite ways to do it is to temporarily break the offending loops, which can be sometimes a bit dangerous, but fortunately linear power supplies usually don't self-destruct themselves when you do that, unlike switching power supplies, which always like to self-destruct anyhow, but that's a story for another video. Anyhow, in our lucky case, it's easy to disable the current limiting loop. We just remove diode CR9. We should be left with the primary voltage regulation loop only, which is enough to operate the supply. If the current limiting loop was a culprit, that should temporarily fix our unit. There you go. Alright, so diode disconnected. So see if it oscillated and then triggered the current protection, or if it's the current protection that triggered the oscillation. That's the experiment. There we go. So we go up, we go up, we go up, we go up, we go up. Ha! It still oscillates. Oh, it's even worse. So it's not the current protection. Actually, the current protection was saving it. It is something in the master regulation. Okay, we learned something. Okay, so now what's in this loop that could cause it to oscillate? There's no other caps in here except over here. There's this guy, the 47 microfarad, and this might be dead. C9, we have to find where C9 is. Would be this fellow close to the current sensing resistor on the output. And I remove the cap in question, and sure enough, 426 picofarads, so that's dead, and that's the filtering cap at the output right there. So that might be the cause for our oscillation. So let's replace that one, and actually the other ones that are in there while we are at it. So result of the investigation, these are the original caps. 2 completely bad, 1 very good. And unfortunately I have very good caps here, the 105 degree C one. So I'll replace with that and see if our life gets better. So those 3 new caps, and this one was in the main power supply. I think that's the one that's causing us trouble. The 2 other ones were in the ion pump current monitor, and they are both in parallel, and one was still working, so this fault didn't cause probably any trouble at all. But let's see if that one repaired our board. Let's not put a load on it, see if it's stable without a load at all. And I'll do the same as before, bring it up slowly. There you go. Starting to regulate. In regulation, 18.64 volts, that repaired it. So now we have a good primary power supply. Let's work on our current source. Okay, so I'm now looking at the resistor that represents my coil, and I expect 10-15 milliamp. So that should be 10 to 15 millivolt DC since it's a 1 ohm resistor. If I turn it on, 11 millivolt DC, goes up, goes down, so it's working. 10.5, there you go. And it's much better. On the scope, it looks ugly, but it's way less ugly than it used to be. I'm at 30 millivolts here instead of 200, and the noise is picking up from here. So that's much more reasonable. Now I am monitoring the output voltage with and without the load, and that's not a problem. That's super well regulated. So I have a very stiff, well controlled power supply now. Okay, I'm now reconfigured to measure milliamps. And then we seem to have a problem with Ohm's law, because I get 23 milliamps. I wasn't expecting that, so maybe my resistor was not 1 ohm anyhow. And it's not moving with the load either. My circuit is working plenty fine. And by the way, there are other capacitors on the board, but they are 10 lumps. And I checked them and they check good, so I think it's fine. So I'm back with the board in it. I'm measuring 13 millivolts, and now it looks better. It moves a little bit when I remove the light, but from the experiment I had on the bench, I don't believe it's actually the power supply. It's my measurement is the return to ground that picks up a microvolt less or more in current when the light is on. But it looks steady. I don't know if I fixed anything really, but I definitely discovered that HP knew that there was an issue with the design of a current source, and they fix it in the later clock. So I better go look at the other clocks, find all the bad caps and see if I can upgrade their current source for the C-Field. And by the way, there's also the main filter cap here, and I did check it. It retained all its 2400 microfarads, so it's fine. In fact, the freaking cap was so good that it preserved a lot of residual voltage on it, and I ended up zapping my BNK LCR meter. Not to worry, we have repaired it since in another video. Probably want to replace it at some point, but at this point the machine seems to be behaving as it should. So I'm going to button it up and check my other clocks to see if they have the same problems. Well, I opened up the second clock. It has the same board, the exact same one. I can get it out. So guess what? I'll check for the same caps and see if it has the same problem. Well, that's somewhat interesting. I haven't taken the capacitors off yet, but maybe you can tell this has been replaced. And this is the voltage reference, the 10 volt voltage reference. So somebody has already been in there before me. And the one. This guy, dead. 800 puff. And here's number 2, and it's equally dead. And any bets for number 3? Completely dead too, so 3 out of 3. And 1. Alright. 3 new caps. Okay, that should be good. I'll redo a full test of it on the bench. Also test the tantalums in circuit while I'm at it. Yeah, 15 micro, 15 micro, 15 micro, okay. Tantalums, good. Perfect, no noise on the thing. Second thing to check is that if we got a good voltage reference. And we have 10.0047. And then finally we have to check our milliamps. Alright, 17 milliamps. I'm going to turn it down by 2 volts, didn't budge. Some more volts, I am at 23 volts. Still the same. Go to 29 volts, still the same. So I think we got it. This one works fine. And also the main filtering cap. It was good on the other machine, so I expect this one to be good too. And it's off the charts. 2.7 millifarad, so 2700 microfarad, and it's supposed to be 24. So 2400, so it's good. Okay, let's see if we're back in business. Get the 2 clocks started and try to rely them on top of each other.
20 minutes later.
Lots of beam current. Second harmonic's a bit low, but because yeah, so yeah. Ooh, I was far off. There we go. Alright, somewhere here. Operate. Logic reset. Locked. Oh, unlocked. I was probably not close enough. Why did it go so far off? It's probably because I changed the power supply. Yeah, okay. Come back to me. Oops. Bring that back in the middle. Should be good, but I'm not. What is that? There you go. Took a while for the loop to adjust. Okay. So now we are locked and the control is 0. And I had a lot of adjustments to do, so my guess is that now that the power supply is repaired, both of them are out of whack a bit. We'll see. What about this one? Clock number 4. Lots of second harmonic. So I should be pretty close. So here's the max. There we go. And yeah, it's on 280, so very close. Put it to operate. And there's lock, it's right in the middle. Okay. 2 locked clocks. Okay, so we're back into business, and the clocks seem to be pretty much on top of each other so far for the first 15 minutes. They are still at 100 picoseconds apart. And so I'm doing the 2 clocks that we repaired. This one, that's a 3rd repair now. And the other one in the back has just had one repair. And then we have this one, which we have repaired other things, but not the power supply yet, so that needs to be checked. So we're going to see if that helps any. Alright, looks like we are going somewhere. Took me a little while to find the right C-Field, but this is about 12 hours, and we have 1.6 nanosecond of deviation between the two, and I think Einstein's smiling.
2 days later.
Well, we're doing fairly well here. Look at that. Started over here a while ago, 3 days. And we are at 4.4 nanoseconds after 3 days, which is the best I have ever had here. And you can see it's breathing a bit. It gets a little positive here. Did an excursion to 3, then went back down, then negative, then here we had a little bit of an excursion to 4. So it's waving up and down, which is why they took not 1 clock but 4 clocks when they did the thing. So we seem to have improved the situation significantly while making the YouTube recapper crowd happy. Whether this is enough of an improvement still remains to be seen. And then I went into another clock, the only unit in our collection that's equipped with the high performance tube. It had already failed on us and we had to repair the multiplier in another episode. But sure enough, I now discovered that it also had the same improved C-Field board and that its 3 electrolytic caps were toast too. How predictable! Which leaves us with one last clock, which I had given up on after the dreadful first experiment. That clock was literally all over the place. But now that I have gained more confidence into repairing these clocks, I think I will give it another chance, but that will have to wait for another video. See you then!